This is the second part of the confidence intervals with a t-distribution. We will go to the proportions confidence intervals with the hypothesis testing. Now, confidence intervals that we looked at last time involve the z-distribution, in other words, the standard normal distribution. The difference was that in the standard normal distribution, we assumed normality, and also we knew the population standard of deviation. Well, what's the difference between that z-distribution, or the standard normal distribution, and the t-distribution? Well, the t-distribution, you still have to assume normality. However, you do not know your population standard of deviation, or you do not know the approximation by a large n, a large sample size. So therefore, we use the t-distribution when we do not know our population standard of deviation. Our formula for the z-score is this, to find our critical test value, our test value, not our critical value, but our test value. Our t value will be this one. Now, the t distribution differs from the z distribution in the sense of you have to use degrees of freedom. Degrees of freedom is how much can the data vary when you're doing a mean. It can only vary by 1. It can only be changed by 1. What that means is when you look at degrees of freedom, you take your sample size and subtract 1 from that, n minus 1. That will give you how many degrees of freedom you have. Let's look at see how we find a t-distribution. Before we do that, though, notice the difference. The normal distribution requires a population standard of deviation, whereas the t-distribution does not require a population standard of deviation. You can have a sample standard of deviation instead. Now let's look at how to find a t-distribution. But before we do that, let's look a little bit more about the t-distribution. Now notice this one. This is your normal curve, your standard normal curve. Your t-distribution is a little bit flatter and is dependent on how many samples, how much of your sample size you have. The bigger your sample, the bigger your degrees of freedom, the more similar to your normal is going to be. In other words, let's look at this. Here's your standard normal. Here's a t-distribution with degrees of freedom of 6. In other words, your n is 7. Well, let's increase that sample size. Let's increase it by 12. 12 minus 1 is 11. Your degrees of freedom are 11. And look at this curve. It looks more and more like this one. You increase your degrees of freedom to 23, and notice how you have that. So you keep increasing your degrees of freedom. The higher the degrees of freedom, the closer this t-distribution is going to look like the z-distribution. Okay, that is another reason why they say that if you have a very large sample, then you can approximate using the standard normal. This was more relevant in the old days when all we had were tables and we didn't have calculators like we have right now. Okay, so let's look at this. As the degrees of freedom increases, the t-distribution gets closer and closer to a z-distribution. Let's learn how to read the t-tables. Let's say that I want to find a t-critical, or a critical value for t, for 95% two-tail with an n equals to 10. What is our degrees of freedom? If you said n minus 1, which is 10 minus 1, which is 9, you would be correct. When we're looking at our alpha, what is our alpha? Well, what is the area in between the two? Well, 1 minus 0.95 is 0.05. We also look for the t-distribution where you have two tails, and you get the alpha for two tails. What if we were looking for a one tail? Well, remember, this 0.05 is on both tails, so we would have to divide it by 2. So 0.05 divided by 2 gives you 0.025. This is a review from Chapter 6, Central Limit Theorem and Inverse Norm. Now, let's look at this. What is the t-critical that we need for this? We got to go to our tables. You go to our t-tables. Now, to go to your t-tables, you go for where it says the two-tail alpha. That will be the 0.05. That's already including the two areas on the two sides of the graph. you go down to where your degrees of freedom are 9, and you find that number. This is your critical value, 2.262. So the critical value that they talk about is 2.262. Once we have that critical value, what we do is we continue the process. Now, let's look at this one right here. Let's try to find, with a sample size of 13, an alpha of 0.01, it's a two-tail. What is your T sub alpha divided by 2? Okay, let's look at it together. What is our degrees of freedom? If you said 12, that is correct. What you do is you go to your T-tables. Now, what I'm going to do is I'm going to go over to my T-tables right here. Okay. Let's go to the T-tables. I thought I had put them in there. So we go to where we have our sample size is 13. So we go down here to our T-tables where we have degrees of freedom, and we want 12 degrees of freedom. So we go over here to 12. Now, look how you have one tail and two tails. Now, notice this. If you want a two-tail alpha, 0.01, what you're going to do is you're going to go over here to two tails and look for 0.01. And here it is. Here's 0.01. So look at the intersection between 0.01 and 12. So this is going to be the intersection between 0.01 and 12 for two tails. And you get 3.055. That's your degrees of freedom for a 13 sample size and a two-tail of 0.01. What if your tables didn't have the two tails, it only had one tail? Well, what you would have to do is take that 0.01 and divide it by 2. So we have 0.01 divided by 2. 0.01 divided by 2 will give you 0.005. You go to the one table and you go to the 0.005, and it's right there. At 12 degrees of freedom, again, you get the same number. Okay? So either way, you get that your T-table, your T-value, your critical T-value is 3.055. And that's how you find your critical value for T. Okay, let's go ahead and look at the rest. So now we're going to go ahead and continue. Who developed the T-distribution? Well, this part is not going to be on your test, but it is an interesting thing. It's William Gossett. He was born in 1876, and he died Okay, so William Gossett developed the student T-distribution. It was developed, when people develop new ideas, it is often named after the person. For example, why is it student T-distribution? Well, Newton developed the law of cooling, so it's called Newton's law of cooling. Einstein's theory of relativity, René Descartes, the Cartesian coordinate system. Why is it called the student T-distribution? Well, William Gossett developed the student T-distribution, and why isn't it called the Gossett distribution? Well, he was employed by Guinness Brewery employee in Ireland. He was employed by Guinness Brewery. He needed distributions for small sample sizes. He developed the T-distribution. However, the brewery employees were not allowed to publish. So he published it anyway under the pseudonym of Student T. That is why it's called Student T-distribution. Now, the formulas for the confidence intervals on the mean, they're pretty much the same as the Z-distribution ones. The only difference is, instead of using the Z, you use the T, and instead of having a population standard of deviation, you have a sample standard of deviation. So, our formula is, first of all, we know that it's normally distributed, but we don't know the population standard of deviation. Now, if your sample size is bigger than 30, it can be approximated, but it's better to use the T-distribution. Now, let's look at the formulas. The formula for your margin of error is your t value, your critical t value, times your standard of deviation divided by the square root of n. After you find your margin of error, you're going to add it and subtract it from your mean in order to find the two limits, and these two limits will tell you the distance, the range of values that you could have to be your population mean. In other words, that range of values, your population mean could be in there, and it will tell you how much from your confidence level. In other words, if you had that interval and it was a 95% confidence interval, then there would be a 95% chance that that population mean would be inside of that range of numbers. Let's look at this right here. Let's look at this example right here. The weights of women who join a health club are normally distributed. 7 women are randomly selected, and their weights in pounds are recorded. Construct a 99% confidence interval on the mean. Okay, so you have 120, 135, 150, and so on. Our first step is to find our numbers. What numbers are we looking for? Well, we're looking for the sample mean. We're looking for the sample standard deviation, because this time they don't give you a population standard deviation. And you're looking for the sample size. You find your t critical by using the 99% confidence interval or confidence level. So let's start this. First of all, we go ahead and put our information in the calculator, and we enter these into the edit mode, into L1. Then we go ahead and press Stat, Calc, one variable stats, and we find our information. What we need to pull out of this screen is your mean, which is 142.1429, your standard of deviation, which is 27.5162, and your sample size, which is 7. After we do this, our next step is going to be to use these to calculate our t values. Okay, so now, our margin of error. So now our next step is going to be to go ahead and construct our t values. Okay, we need to find the t critical for a 99% confidence interval. In order to do that, you must find the alpha. Your alpha for 99% would be 1 minus 0.99, which is 0.01. Now, if we want the 2 tails, just take that 0.01. If you choose the 1 tail, then you would have to divide that by 2, giving you 0.005. Either way, when you go down to the degrees of freedom, since you have a 7 degrees of freedom, your sample size is 7, your degrees of freedom will be 6. Let's look at that. Okay, so we look at this. Your degrees of freedom are 7 minus 1, which is 6. We go to our t values. Okay. We go to our t values right here. So 6 is your degrees of freedom. 2 tails, 0.01. It's going to be here. So that's going to be what? So we have, oops, that's not it. Here we go. So we have 99%, that's 0.01, okay? So we go over to 0.01 on 2 tails. Now our sample is 6, our degrees of freedom are 6. So you go 0.01 and then 6, and you get what? 3.707. Okay. So basically, your t value is 3.707. So we choose this number, 3.707. We multiply it times our standard of deviation, 27.5162, divided by the square root of your sample size, which is 7. Once we find this number, this E of 38.5533, we add it to the mean to find the right limit, and we subtract it from the mean to find the left limit. We get the higher limit and the lower limit, and that's our confidence interval. What does this mean then? Well, this means that I can say with a 99% confidence that the mean weight of women who join the health club is between 103.6 to 180.7 pounds. And that's how we would do this problem right here. Okay, so let's look at the next one. Okay, so let's look at this one. A random sample of dogs is taken and the length time in minutes required to teach the dogs to do a trick is recorded. Construct a 90% confidence interval on the mean time to teach the dog the trick. Okay, well, we have to look for certain things. We have to look for our sample mean, which was 26.7. We look for our sample standard deviation, which is 4.2, and then we look for our sample size, which was 39. Now, does it say anywhere in there that it's normally distributed? No. But why can we accept that it's normally distributed? Well, look at that sample size. The sample size is 39, so it's greater than 30. So by the central limit theorem, you can assume normality. However, you do not know your population standard deviation. Therefore, you must use the t-distribution. Okay? So now, we're going to continue this. In order to do this, our first step is to find our E, our margin of error. In order to do that, we need to find our t-critical for 90%. Well, what is our degrees of freedom? 38. This becomes a problem when it comes to tables. Now, some of them will have it, and some of them will not. You're looking for 38 degrees of freedom, and then notice that this one does not have it. Okay, so we have one that has 38 degrees of freedom. Well, we don't have it, but we can find it in other tables. Now, just to tell you, the degrees of freedom, 38, and your t-value will be about 1.686. Your tables that you will be given and the t-values will correspond. There will also be ways of doing this without having to do it through the long way. You probably saw this already in class, and I will show it again in this example. Anyway, we find the t-value to be 1.686. Our sample standard deviation is 4.2, and our sample size is 39. We enter these values and we find our margin of error. Now, we find the upper limit by adding it to the mean, and we find a lower limit by subtracting it from the mean. And then we get our confidence interval that's going to be between 25.6 and 27.8. So I can say with a 90% confidence that the mean time to teach a dog a trick is going to be between 25.6 and 27.8. That would be the answer. Now let's look at the other way that you could do this. Okay? So the other way of doing this is through the calculator. Let's go ahead and look at the calculator then. Let's turn on the calculator. Now, I'm going to expand this a little bit. We're going to turn it on. Now, to find the confidence interval for the t-distribution on the calculator, press Stat, go out to Test, go out to, instead of z-interval, go to t-interval. See right there, the t-interval. Choose Stats because you're using information that's already been given to you. Your mean is going to be 26.7. Your standard deviation is 4.2. Your n is 39. And your C level is going to be 0.90. You calculate, and you get your answer. Your answer is going to be that it's between 25.6 and 27.8, which is close to what we had. .6 and 27.8, right there. So you can use the calculator to do this. Now let's try this one. The temperature in degrees Fahrenheit of a species of aliens is normally distributed. A random sample of these aliens is taken and their temperatures recorded. Construct a 95% confidence interval on the mean temperature of the alien species. So, did you choose the following 1, 2, 3, or 4 as your answer? Okay, 2 is the closest thing. I have in my calculator 64.548 to 71.034. The closest thing is number 2. You will get some differences in answers in the sense of sometimes if you use it by calculator or by long way, you'll have a minimal amount of difference. This should be accounted for, and it will be accounted for in the test. Okay, so basically that is it for confidence levels using the t-distribution. Our next thing will be hypothesis testing, and hypothesis testing with a t-distribution, and then we'll do another one with the proportions. Thank you.